when we were talking about solving a system of equations, we listed out graphing as the first method that you learn because it really helps you understand what solving a system of equations is all about. You're finding the point of intersection of both of those equations. You're finding the ordered pair that satisfies both of them. However, even though it's the first thing that you learn how to do when you're solving a system, it's not always the most convenient way to find that point intersection. We need some other methods. Here, let's take a look at some of those problems down here, like for example, 63. On 63, this one's not set up to graph this thing conveniently. And even if it was, or maybe I rearranged some things and I put it in an order that would be easy to graph, let's say by putting it into slope-intercept form like this, it may not hit exactly on grid marks, and I might be having to guess where that point of intersection is. So it is not, on this one, the most convenient method. Graphing is definitely not for that one. So what would be? We need some other methods, something that we could solve this thing by hand. Now, as far as it goes, if I have access to something like Desmos, you could very easily type in both of those equations and you can find that point of intersection. The problem is that when we're talking about standardized tests and when we are in our honors math courses here at Gardner High School, one of the goals is to help you prepare for those standardized tests like the ACT, the SAT, and any of the AP exams. And some of those, most of those, none of those allow you to use something like Desmos. Sure, you can use a graphing calculator, but if you're going to use, say, the TI calculator, putting this in the calculator, well, you've got a little bit more work because it has to be in y equals form. So I'm thinking that there's a more convenient method than graphing on this one. What could it be? Could it be something like our second method here, which is substitution? And substitution is a super important principle in mathematics that goes like this. If two things are equal to each other and I've got an equation that has one of them in it, I could take it out. Let's say I take out my x value here, and then I could replace it with something that's equal to that quantity. That's what substitution is all about. I take something out and I substitute an equal quantity in its place. And even though this is set up to solve by graphing, because that's how I made it, I can solve this thing by substitution because it's set up to do that too pretty easily. What I would do is I would take this negative 3x plus 9 and I can substitute it in for y because that's what it's equal to. It says y is equal to 3x plus 9, which means I can take this y out and replace it with negative 3x plus 9, and thereby solving that system of equations. And let's see what happens whenever I do that. I'm going to take out the initial y, the red y, and replace it with a negative 3x plus 9 is equal to, and then the other part of the equation stays exactly the same. I've got 1 half x minus 5. And let me move this down just a little bit so I can label that we're doing this thing by substitution. All right, okay, there we go, substitution. And now what I've just done here is I've gotten rid of my y, and now I have a linear equation that just has x's in it, and it's super easy to solve. Even though this one has a fraction in it, I could pretty easily get rid of it. There's only one fraction. If I multiply by the denominator of 2 on both sides of this, all my fractions are going to disappear, and it'll be that much easier to solve. Okay, so if I multiply, now I got to multiply everything by 2. Over here on the left-hand side, I'm going to have a negative 6x plus 18 is equal to, and then over here on the right-hand side, I'm going to have 1 half times 2 is just 1, so 1x, and then minus 10. What I tend to do whenever I'm solving a linear equation is I want to keep my variable positive, and I can keep it positive by adding the 6x's over here. Sure, you can subtract the x over to the other side, but it's going to make your x negative, which is not necessarily a problem, but there's more chance that you're going to commit some kind of sign error further down the road. So I like to try to keep it positive. So we're going to add the 6x's over to the right-hand side, bringing everything else down. So I'm going to have 18 is equal to, let's turn it into like a Khan Academy video where I'm color coding everything. Anyway, is that right? Yeah, that's right. And then finally, I'm going to take the 10 and I'm going to add it over to the other side, and that's going to make a 28. So 28 is equal to 7x. I'm going to keep it consistent now. I've already committed to it. And then finally, divide both sides by 7. And I'm just going to switch up the colors now. And that's my 4. Hey, look at that. That looks familiar because that's exactly what we got whenever we solved it by graphing. And that should happen. No matter what method that you choose, you should still end up with the exact same answer. Now, your work is only partially done, though, because you've only found x is equal to 4. You have to now substitute that back into one of the other equations so that you can solve it for the other variable, in this case y. And it doesn't really matter which one you choose because they're both going to give you the exact same answer. So you choose whichever one you feel is going to be easier. I look at this, it's got a fraction. This one doesn't have a fraction. I'm probably going to choose the second one here. So if I take my y is equal to a negative 3 multiplied times 4 plus my 9, negative 3 times 4 is negative 12. Plus my 9 is negative 3. And of course, that's exactly what we had for our y value there. So we just solved this thing by substitution. And now, again, you don't want to solve every system of equations by substitution just because you're trying to avoid graphing. It's just, is it convenient to solve that thing by substitution? This one was because you had y already isolated, so it's very easy to stick negative 2x plus 9 in its place. Not always the case. So if it's not that it's not set up in that kind of way, like number 63, then the next thing that you go is, can I easily get the x of the y by itself? And on 63, you actually can. This y has a leading coefficient of 1, so you can just subtract over the 0.5x, and you could pretty easily stick it into, let's say, the other equation, and just have x's and solve that system equation from there, right? Okay, so I'm only going to do substitution when it's convenient, and it's going to be convenient when one of your variables is already isolated, or it's going to be very easy to isolate that variable without making your equations even more complicated. They're going to get more complicated if you have to divide by something, and when you divide by something, you're going to create fractions. If you look over here at 64, neither one of these equations is it going to be easy for you to solve by substitution. And the reason why is, let's say that I choose to solve this thing for x. If I do, I'd have to add the 5x's over, divide everything by 6. Now everything has fractions in it. And the same thing is going to be true for the y and the x and the y in the second equation. And the reason why is because the coefficients, they don't have common factors that are just going to cancel out. The 6 doesn't go evenly into the 5 or into the 9. And then likewise, none of these, either the 9 or the 7, is going to go evenly into the 15. This one would be terrible to do by substitution, which brings us to the final method, which is elimination. Number 3, elimination. Elimination? I don't think that's how you spell that. I think that's how you spell it now. Elimination, the goal here is to, it's right here in the word, eliminate one of your variables, either the x or the y. Sometimes it's very straightforward. All you have to do is add the equations. Poof, x's disappear. That's not always the case. Usually you have to add or subtract a multiple of the equations in order to get one of those variables to disappear. Let's go back to our system of equations that we started this whole thing out with. And usually when you do elimination, they're not in this form. They're not in slope-intercept form like this. They're usually in standard form. So what I'm going to do is I'm going to rewrite my equations in standard form so that we can see an example of solving this thing by elimination. So my first one was y is equal to a half x minus 5. Now, in standard form, we usually don't like to have fractions in it, so the first thing I'm going to do is multiply everything by 2. And I'm going to have a 2y is equal to 1x minus 10. And then finally, I would subtract this x over, so I'd have ax plus by is equal to c. I would have a negative x plus a 2y is equal to negative 10. Now, some people look at this and go, no, 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 you can't have a negative out front. You actually can. It really doesn't matter. I actually don't like it, so that's why I usually get rid of it. So for those of you who are throwing fits right now, just multiply everything by -1. And you can get rid of that leading coefficient if that's your thing. Minus 2y is equal to a positive 10. Okay, so here's our first equation in standard form. Let's do the exact same thing for the second one, which, if memory serves, is y is equal to a negative 3x plus 9. Now, there's nothing fancy to do on this one because we have no fractions. All I have to do is add the 3x over to the other side. So I have a positive 3x plus y is equal to 9. And then here's my second one in standard form. So now let's look at this solved by elimination. Okay, so I'm going to list out my two equations, stack them on top of each other, and 3x plus y is equal to, what was that, 9? Yeah. Okay. Now, again, the goal here for elimination is to eliminate, to get rid of either the x's or the y's. In order to do that, they have to have opposite coefficients. This one's a 3, but this one's a 1. They're not just going to eliminate if I add them. This was a -2, this one's a 1. Again, they're not going to eliminate if I just add the equations together. So what I'm going to have to do is multiply one of the equations by some sort of constant. Sometimes it's one equation and sometimes it's both in order to get those numbers to match up. Now, what some people do is they just try to get the coefficients to match exactly, and then they subtract the equations. I'm going to suggest that you don't do that, and let me demonstrate why that's the case. Let's say that I've decided to get rid of the x's, and I go, oh, I just need to multiply this top equation by a positive 3. So let's do that. So I'm going to multiply this by 3. Make sure that you multiply everything by 3. You'd have a 3x minus 6y is equal to 30. And then the bottom one stays the same. Plus y is equal to a 9, right? Okay. Now then, if I were to solve the system equations by elimination, you could see very clearly that I'm trying to eliminate my x's, and the only way that I could eliminate it is if I subtract the bottom equation from the top equation. And now with the x's, that's not that big of a problem because I know that those are supposed to eliminate. But where the problem comes in is with the y's. I have a -6y minus a positive y, which this negative is going to mean that I actually combine these up to make a -7 of them instead of a -5 of them. And that's where the error sometimes comes in. Very easy to make a mistake right there whenever you subtract it. So my suggestion instead is to multiply this thing by, maybe this over, a -3. That way these coefficients are actually opposites from each other, and then you add the equations instead of subtracting them. So let me fix this. All that's going to do is change all the signs up here, negative, positive, and then a -30 right there. Okay, so now whenever I add my two equations, my x's cancel as I intended. Then I have myself a 7y is equal to a -21. Divide y is equal to -3. Was y equal to -3? It was, yay. So we've done our work correctly. Now, when I look at this though, I probably would not have eliminated the x's. I would have eliminated the y's for two reasons. One of them is that the coefficient is a little bit smaller, but the other one is that they're already opposite signs, so I wouldn't have to multiply by a negative. All I'd have to do is multiply by a +2 on the bottom equation. Okay, but since I've already done it, I'm just going to stick with it. And just like the substitution method, This one's not quite done until you take the y and substitute it into one of the equations. It could be one of the original equations, or it could be the modified equation after you've multiplied by whatever your coefficient is that's right there. So I'm going to actually plug this one into the top equation to get my x. So I'm going to have x minus 2 times a negative 3 is equal to 10. X plus 6 equals 10. Subtract the 6 over, x is equal to 4. And now I have my x and my y coordinates, and I'm done. So the elimination gives us a third possibility of solving a system of equations. And again, it's when do I do it? So let's look back at, let's say, question number 64, that was right here. On 64, we already talked about how substitution is totally inconvenient to do on this one because it's going to be tough to isolate either the x or the y in either equations without creating something that's going to be tough to solve because of all of the fractions that we create. So instead, elimination is probably the best method to use on something like that. In the next video, we'll take a look at each of these in turn and try to figure out what's the best method and give you some tips on how to solve it.